Welcome to section 7.6, Logistic Functions. At the end of this video, we should be able to answer these questions. What is a logistic function? What are the key characteristics of a logistic graph? What is the general equation for a logistic function? What are some real-world examples of logistic functions? How do we solve for a particular logistic function given data or a graph? Well, let's talk about what a logistic function is. A logistic function is a graph that looks like this, which has a lower bound and an upper bound. We start low, we have this rapid increase in the values of y, similar to an exponential graph, and then halfway through our journey from the lower bound to the upper bound, our graph starts to slow down and changes from a concave up graph to concave down, eventually leveling off at this upper bound, which we'll call C for the purposes of discussion. So halfway through this graph, we have this point of inflection where our concavity changes from concave up to concave down. Now let's talk about what type of equation would generate this type of graph. Here's the general equation for logistic functions. It's in two forms, one with a base of e being used and one with a base b. You'll see that our f of x has this value on top, c, over 1 plus ae to the negative bx, or c over 1 plus ab to the negative x, where a, b, and c are constants. So these are the three unknowns we would have to solve for in given a set of logistic data. The domain is all real numbers. Let's take a moment and see why this equation generates this graph. Let's think about what happens as x gets larger and larger to this expression. Now as x gets larger and larger, we're multiplying it times a negative number. And any number raised to a large negative number becomes very, very small. In fact, so small we could almost consider it to be 0. So we end up with a times a number very close to 0. So 1 plus a very small number. C over that number would just end up being basically c. Now if x were a negative number, then we'd be multiplying a negative times a negative here. And e to a very large positive number, when x is a large negative number, becomes a large number. So I'm adding 1 to a very large number. So c gets divided by a very large number, eventually becoming very, very close to 0. So if we go back to our graph, you can see that as x gets more and more negative, we're dividing by larger and larger numbers and eventually getting very, very close to 0. And as x gets more and more positive, we get closer to having c divided by 1. So our graph levels off at y equals c. Populations are good examples of how this type of graph plays into the real world. Most populations start out with a very few members of the society, and as they take advantage of the resources around them, the population grows and grows rapidly in an exponential manner. But as the population grows and demands more and more resources, the environment can't supply the necessary resources to sustain that growth, so the growth slows down until we reach this equilibrium where our population and our resources match exactly. Now let's talk about how we would solve for a specific equation given a set of data. Here's a good example of how logistic growth might appear in the real world, where we start out with slow growth, it increases very quickly, and then levels off again. A new subdivision with 1,000 lots shows the following growth in population. Here we have our months for the time period, and the number of houses sold or built on this lot. So what we want to do is use the points for 2 months and 10 months to find the particular equation of the logistic function that satisfies these constraints. Now notice that we're only being asked to use 2 data points, but in our equation there were 3 unknowns, A, B, and C, which means that that third piece of information is given to us somewhere in the question. And where that's given to us here is right here where they tell us this 1,000 lots. We can't sell more than 1,000 houses, so that's going to be our upper bound, our C value for this particular equation. So that tells me that C is going to be 1,000. From there, we're going to take the same approach we have with every other type of equation in this chapter. We're going to take our 2 data points and plug them into our general equation. Let's use the secondary equation here and solve for A and B. So our general equation is y equals c over 1 plus a times b to the negative x. And we're going to plug our values in. We'll start with the x equals 2 months. So we have 103 houses equals 1,000, because that's our c value, over 1 plus a b to the negative 2. Now, our second equation is the data point for 10 months. So 167 houses were sold after 10 months. So that's 1,000 over 1 plus ab to the negative 10th. Now, we need to use these 2 equations with 2 unknowns and solve. So we're going to have to use our techniques, either elimination or substitution. Elimination, well, let's see where these 2 equations lead us. Let's start by moving our variables out of the denominator for each of these expressions. So I'm going to multiply my first equation by 1 plus ab to the negative 2 on both sides. So we'll put it right here, ab to the negative 2. So that gives me, I'm going to come down here, 103 times the 1 plus ab to the negative 2 is going to be equal to 1,000. And then if I do the same thing with my other equation, I'll see that I have 167 times 1 plus ab to the negative 10. And that's also going to be equal to 1,000. Now we have to get to our variables. So what I'm going to do is I'm going to divide both sides by this coefficient here. So I'll have 1 plus ab to the negative 2 equals 1,000 over 103. And then I have 1 plus ab to the negative 10 equals 1,000 over 167. Now I'm going to subtract 1 from both sides on both of these equations. So I have ab to the negative 2 equals 1,000 over 103 minus 103 over 103. You can do this with your calculator, but it's always good to practice a little mental math. And ab to the negative 10 equals 1,000 over 167 minus 167 over 167. So 1,000 minus 103 should be 897 over 103. And 1,000 minus 167 should be 833 over 167. And here I need to find some way to combine these two equations and solve for one of the variables. So if I divide, I'll be able to eliminate my a values, and I subtract my b value exponents. So negative 2 minus a negative 10 gives me b to the 8th, and that's going to be 897 over 103 times the reciprocal of the denominator, so 167 over 833. And then to solve for b, I need to take the 8th root, or raise it to the 8th power. I think that's a little beyond my mental math capabilities, so let's pull out our calculator. So let's pull out our calculator and figure out b. So first, 897 divided by 103, and I'm going to multiply that by 167 divided by 833, and then I'm going to raise that to the 1/8. So my b value is 1.072. Now that I have b is equal to 1.072, I can go back into my original equations and solve for a. So I'll use my first equation, where I've got this set up as 1 plus, or ab to the negative 2 is equal to 897 over 103. But I know that b is now 1.072, so a over b squared is going to be a over 1.072 squared, and that's going to be 897 over 103. So a is going to be 897 over 103 times 1.072, or b squared. So let's pull out our calculators one more time. First, let's move this over. So if I take this previous number and square it, and multiply by 897, and divide by 103, I should get a. So a becomes 10.011. Let's go back up and see if that's what we ended up with. Whoop. 10.001 and 1.072. Okay, now that we have our logistic function, we want to predict the number of houses that will be occupied at the value of x corresponding to 2 years. Is this interpolation or extrapolation? Well, let's put these values into our calculator, and then we have to recognize that this is actually a bit of a trick question, because when they say 2 years, we have to recognize that x was originally given to us in months. So our 2-year value for x is actually x equals 24. So let's start by putting this equation into our calculators. Let's go to y equals, and we'll put in our equation 1000 divided by the quantity, make sure you put this in parentheses, 1 plus 10.011, another parentheses, times 1.072, close that parentheses, raised to the negative x, and drop back down and close the parentheses one more time. So there is our function in our calculator. And now I'm going to go back and evaluate it using my vars, yvars, function y1 of 24. Here we go. 346 of our houses will be sold after 2 years. So y of 24 is approximately 346 houses. Now the final question is this interpolation or extrapolation? Well, since our x value of 24 extends beyond the values given to us in the table, which only go up to 10 months, our value lies outside of our data set, so it must be extrapolation. Alright, let's recap. What is a logistic function? Well, a logistic function is a function that has both an upper and a lower bound, where it transitions from your lower bound, shows exponential growth until it reaches a point of inflection, and then the growth slows down and levels off at the upper bound, which we call C. What are the general equations for a logistic function? Here they are. F of x equals c over 1 plus ae to the negative bx, or f of x equals c over 1 plus ab to the negative x, where a, b, and c are constants and the domain is all real numbers. What are some real-world examples of logistic functions? Well, just about any population growth that has the potential to experience limited resources after time, as time passes. So parameciums in laboratory cultures, Daphnia populations, or even fur seals, where their resources strain their populations. Finally, how do we solve for a particular logistic function given data or a graph? Well, we're going to need 2 distinct points and a value for the upper bound, the C value, to allow us to come up with a specific equation. We'll take the same approach we did in the past, where we plug in our 2 data points and solve for our 2 unknowns. Here we do have to take the extra step of removing our unknowns from the denominator before we can attempt any substitution or elimination.